Okay, guys, so yesterday we looked at displacement and velocity, and today we're going to look at acceleration. Okay, so from what we've done last term with calculus, right, acceleration shouldn't actually be all that difficult for you to understand. Okay, so what we did when we started with differentiation is we thought about how quickly things change, right? And if we wanted to find in instantaneous rate of change, we could find the gradient function and plug in an x value and get the rate of change out. Okay. And when we started off, right, we thought about this in the relationship of distance and time. Okay. So as you're moving away from your starting position, right, if you take the change in distance over time, that gave us velocity. Okay. But if you think about velocity, right, if we have constant velocity, right, that means that we have, in essence, constant speed. Okay. Except that's not practical in the real world, right? Your car can't go from 0 to 60 instantaneously. That would be awesome, but it's not possible. Okay. So velocity, therefore, the speed also changes, right? And that change is just what we call acceleration. So all acceleration is how quickly velocity is changing. So velocity is how quickly distance is changing with respect to time, and acceleration is just how quickly velocity is changing with respect to time. So if we go back and we think about what we were doing when we were differentiating, right? If I gave you some function, dt, all right, distance over time, right? If you found the gradient function for that graph, you would find the gradient function, which is just your velocity time graph. And if you looked at and analyzed your velocity time graph and we took the second derivative, okay, we differentiated the velocity function, we'd get the second derivative, and that's actually just your acceleration curve. Okay? So when we're thinking about the gradient of velocity with respect to time, we are thinking of acceleration. Okay? And I believe for the most part, we're going to look at constant acceleration. So Kiana, can you tell me what is constant acceleration?
Where the gradient doesn't change. Constant gradient.
Yeah, so your acceleration happens at a constant rate, all right? Zara, can you give me the most fundamentally sound version of constant acceleration? You guys use it in physics all the time. The universal constant for gravity, all right? What is its rate of acceleration?
9.81.
Right, well, we can just, in mathematics, we'll just call it 9.8 meters per second squared is the acceleration of gravity. Okay, that's how quickly you would accelerate, right, in a vacuum, right? Obviously, there's other factors at play. So if we think about acceleration, right, as just a change in velocity over time, all that is gradient, right? Change in a y value over a change in an x value. And that helps us put together the formula for acceleration. Okay, so as you can see, acceleration is just change in velocity over the time taken, right? So if we want a change to the velocity would be your y coordinate. Right? And when we
Morning, Mr. James.
Morning, Dominic.
Sorry I'm late. Edmodo was not cooperating.
Okay, no worries. All right, well, we're recording, so it's okay. You can go back and watch.
Cool.
We're just looking at acceleration, nothing too out there, okay? And I just said that when we were looking at differentiation, when we differentiated this distance time, we got velocity, because velocity was just change in distance over time. And all acceleration is just change in velocity over time. Okay, so you can almost think of that as the second derivative of a distance time function. So if velocity is just change in distance over time, acceleration is just change in velocity over time. That's why it's meters per second squared, because you're taking meters per second, okay? And that's where you get your meters per second squared. Okay? So when if we forget that we're calculating acceleration and we think back to year 7 maths where we were learning straight lines, and you were asked to find the gradient of a line, I would have told you it's change in y over change in x, right? So our change in y is just going to be our final velocity. Take away our change or our initial velocity. Okay? So we have our, you can almost think about this as y2 minus y1 is final velocity minus initial velocity. That will give you the change in velocity component. And then we just need the change in time component. And usually that will be either given to us or it will just be the change in time, right? Which we could calculate using the x-axis if we're given a graph, right? And this is obviously for constant acceleration, because if you think about this, this is the way we calculate the gradient of a straight line. So it's very important that when we use this formula, we remember that this is only for constant acceleration. Okay? Dominic, how would you calculate the acceleration if it wasn't constant acceleration? What would I have to give you?
You'd have to give a velocity time graph.
Not just the graph, but I'd have to give you an equation to that graph as well.
Yeah, you'd have to give the equation, otherwise we wouldn't be able to figure out the acceleration.
Okay, and once I give you that, you've all these powerful tools in calculus that you could differentiate that to find the acceleration function, right? And then you could find the area under that function to find the velocity. So there's many powerful things that we could do if we were given the function, okay? But we're just going to deal with constant acceleration for now. Okay? Right, so when we think about acceleration, right, Kiana, is acceleration a scalar or is it a vector quantity?
Vector. Because it has a negative value as well.
Right, so acceleration is a vector, okay? So in other words, it has both magnitude and direction, okay? So an increase in velocity is positive acceleration, okay? And a decrease in velocity is just negative deceleration, right? The acceleration is happening in the opposite direction, okay? If we have negative acceleration, does that mean that we have negative speed? Zara?
No, you gotta have something that's negative speed.
Okay, so I'm going to kick myself up the butt. What I should have said was, if I have negative acceleration, do I have negative velocity? Sorry.
No, it's an absolute value.
No, well, velocity can be negative, all right? So this poses the question. Okay. I'd like you to quickly have a look for me at Explore 1.2 on page 9, right? We'll quickly explore it together, right? Because it's important that you understand what's going on here. Let's quickly have a look at the cars above, all right? Let's have a look at the little cars, okay? You'll notice both cars are moving in a positive direction, okay? The car's initial velocity is 20 meters per second, and the velocity increases to 30 meters per second, right? So Dominic, what was its acceleration? You'll have to give me.
Wait, which explore are we at?
We're on page 9 in your mechanics textbook.
Because
So
page
just
1.2. Wait,
page
but it doesn't give a.
page
Yeah.
There's a picture
Yes.
of two little red cars and 2 little blue cars.
Oh, it's okay. I thought it was just part of the explore 1.2, like nothing else.
No. We're looking at the cars just above that. Okay.
Okay.
So let's have a look at, if you have a look at the cars above that. Sorry, I don't have it on the screen. If you have a look at the cars just above that, right? And they're just showing you acceleration and deceleration. Okay, acceleration, you can see that the speed has increased from 20 meters per second to 30 meters per second. So there must have been some acceleration in order for that to happen, right? In the real world, we don't just magically get a different speed, right? So what can you tell me about its acceleration? Would it be positive or negative?
That would be positive acceleration.
Okay, now look at the next set of cars, right? Zara, what can you tell me about the acceleration for the next 2 cars? We're going from 20 meters per second to 10 meters per second. What would that indicate?
It would be a negative acceleration.
It'll be negative acceleration. And if you think about that, right, I'll just write it off to the side here. Okay, we don't have the amount of time that this deceleration happened over, but we can still sort of gauge what's going to happen. Our initial velocity, our final velocity was 10 meters per second, right? This is our V, and we're taking away our initial velocity, which was 20 meters per second, right? And you can see you're taking 10 minus 20, you're going to get negative 10, all right? Meters per second, well, we don't know how long this was over, but anyways. Now, with this idea that we can have negative acceleration, but still positive velocity, let's explore part 1.2 together, okay? So the first part says, if the initial velocity is negative, right? So Kiana, what does it mean that my initial velocity is negative? What does that tell you? What's happening?
You're going backwards.
Yeah, you're traveling away from the direction you indicated as positive. So if I say going up the hill is positive, you are going down the hill, or you're going away from the hill in the opposite direction. Okay? What effect would positive acceleration have on the car? Would it be moving more quickly or less quickly?
Less quickly backward.
Right? So I want you to have a look at how we would calculate what's going on. Okay? Oops, sorry. We're going backwards. Okay? I want you to think about this as we're driving somewhere. Okay? So I'm going to draw a little road here for you. This is your start, and this is the shop. Okay? Now, what it means to have a negative velocity is, well, if I say that this is the positive direction, going to the shop is positive velocity, right? Coming back home, this is just negative velocity. Okay? So if I have a positive acceleration, even though I'm traveling with negative velocity, what do you think is actually happening? Let the cogs turn a little bit. Okay. Okay, let's think about this in a different scenario. Okay. I am traveling to the shop. Okay, I have positive velocity. If my speed increases, right, I have positive speed, positive acceleration, right? Will I be moving quicker or slower?
Quicker.
quicker.
Yeah, positive.
Okay, because you've got positive acceleration. Okay. Right, now I'm at the shop. I'm driving home. I have negative velocity just based on the fact that I am now driving in the opposite direction, but I have positive acceleration. Am I going faster or am I going slower? Well, I'm just going faster in a negative direction, okay? Because the negative velocity, when you multiply it by the acceleration, it's still going to give you, the speed is increasing, it's just increasing in the negative direction. Does that make sense?
Yes.
Yeah? So that's one thing with vectors is you need to remember that the minus sign doesn't mean that it's negative. The minus sign is just an indication of direction. Okay? It tells you the direction that something's happening in. Okay? And even though we have a negative velocity, the velocity doesn't mean that we're traveling minus some speed. It just means that we're traveling at a speed in the opposite direction. Okay? And if we apply positive acceleration to a negative velocity, right, it's still going to increase the velocity, right? It's just going to increase the velocity in the negative direction. Okay? Right, this now begs the question that if we have negative acceleration in the same situation, right? We're driving back home from the shop. We have negative velocity because we are driving in the opposite direction to the one we started. What would negative acceleration have on my car, Zara? Would the car be moving quicker or slower?
It would be moving slower.
It would be moving slower, all right? Because we still have deceleration. The speed is decreasing, right? Just something to think about, right? And that you can almost think about is just before you get back home from your car trip, you are decelerating to slow the car down so that you don't crash into the garage. Okay, let's move on. So if we consider that we're only going to be thinking about constant acceleration, right? If we want to think about average velocity, right? If we think about average velocity, right? Dominic, what can you tell me about the average of something? How do we calculate the average of something in life?
You add the starting velocity, I guess, to the ending
Okay,
velocity,
let's not
and then
even
you
think
divide by 2.
Okay, let's not even think about velocity because I want you to very importantly understand why this is the case for average velocity, okay? Here's a simple scenario. There's 4 of us, okay? There's me, Kiana, Zara, and Dominic, okay? If we all write a test, how do I calculate the average for the class?
Well, you just take all the scores, add them together, and then divide by 4, which would be the number of people that did a test.
Okay, so if we think about the average of velocities, we're doing exactly, because it's constant, we're saying, well, we can just take the start and the end. And if we divide by 2, that's the average velocity. Okay.
Okay.
Happy with that?
Yep.
Right. So if we want average velocity, we've said to ourselves that we'll call u the initial velocity and we'll call v the final velocity. Right. So if we take the beginning, we take the end, if we add them together and we divide by 2, we will get the average velocity. Okay. So this brings us back to what we discussed yesterday, right? So yesterday we spoke about this concept of average velocity, okay? So where the velocity might have changed, right? And we said that this is the same as the net displacement over time, right? So again, going back to the fact that if we were given a displacement time graph, right, that was all wonky, okay, and we wanted to find the average velocity, right, we would take just the difference between the starting displacement and the end displacement, and we divide it by the total amount of time, and that would give us our average velocity, okay? But what we've now worked out is that if we have constant acceleration, our average velocity is just a half initial plus final velocity, right? And so just rearranging our formula, right? So substituting average velocity for our new little half u plus v, right? We can work out the equation for net displacement, okay? Just by rearranging our formula. And I'm sure you've seen this many times in physics, right? Raise your hand if you haven't seen this before. So net displacement is just average velocity times time, right? And if we go back to grade 7, Kiana, what did they teach you? How do you work out distance? Distance is just
Speed times time.
Speed times time. And we learned yesterday that if we have displacement, that's just equal to what, Dominic?
Velocity times time.
Velocity times time, right? So here's your velocity, and there's your time, right? Very difficult stuff to understand, hey? I know it's making your brains hurt.
Yes, it's so difficult.
Making your brains hurt. I know it's making your brains.
Yes.
You can imagine the stress that I have planning these lessons.
Oh, sounds so stressful.
Okay, based
At the
on
moment, I'm stressing over filling out some crazy formula.
Okay, based on what we've just done, let's just quickly do these worked examples together. Okay, a parachutist falls from rest to 49 meters per second over 5 seconds. Find her acceleration. Now, before I even do this, I already know what the answer is going to be. Why do I know what the answer is going to be, Dominic? What was my previous job?
Your previous job was to find the average velocity.
No, what was my previous job in life? What did I do?
Oh, your previous job, skydiver.
There we go. So I used to teach people about this. Okay, so I know what the answer is before we even start because, well, you should all know this because this is acceleration towards the ground, and we all know what that acceleration is. It's constant. Okay,
It's 9.81 meters per second
there we go. Okay, but let's say we didn't know that, right? We needed to find it. Okay, we've learned that for constant acceleration, right? And I get a little bit annoyed with the question because it bases it without telling you, it assumes that it's constant acceleration where they should actually specify that it's constant acceleration, because this formula that we're using here does not work if it's not constant acceleration. Okay. So in other ways, we've learned that acceleration is just a change in velocity over time. So final velocity, take away initial velocity over a period of time. Okay. Zara, what's my final velocity?
49.
Okay, and what's my initial velocity?
0.
0, okay, because if something is at rest, it has 0 velocity, and this was all over 5 seconds. So there is your initial velocity, this is your final velocity, and this was over 5 seconds. Sorry, let me get rid of that. And unsurprisingly, what does it give us? 9.8 meters per second squared. What's the actual constant for gravity? Is it 9.81 something something something, or is it 9.81?
Yep. 9.81.
9.8. Is that what you guys use in physics?
Yep.
Yep.
Cool. Okay, so there we have a very, very difficult question solved. Okay. Let's move along. So we have a tractor which accelerates from 5 meters per second to 10 meters or 9 meters per second. And this happens at a rate of 0.5 meters per second squared, right? So that's the acceleration, right? And we need to find the distance covered by the tractor over this time, okay? So when we're looking at this question, we can tell by the way the question's asked, right? Is my velocity ever in the opposite direction, Kiana? Or is my velocity always going to be in the same direction?
It's going to be in the same direction.
It's going to be in the same direction. So when we're being asked to find the displacement, right, or the distance, right, from now on, I'm going to use the displacement equation, right? So displacement equal to velocity times time. This is what we're being asked to find, right? Except we don't have all the information, right? And so we need to work out other bits of information, okay? So the first thing we don't know is we don't know the time, right? We don't know how long this tractor was driving for, right? But based off the information that we're given, we can calculate that, right? So the first formula we can use is we know the acceleration, we know the final velocity, we know the initial velocity, and what we want to find is the time, okay? We have all the other bits of information. So as I'm sure you guys know, in these kind of questions, the big thing is which formula do I need to use to solve the variable, okay? So just get good at remembering all these silly formulas. Right, anyways, our final velocity was 9 meters per second. Our start velocity was 5 meters per second. And our acceleration was 0.5 meters per second squared. Okay. So solving for t, we'll get 0.5 t equal to 4. Okay, that was just multiplying that guy, bringing him up over there. And solving for t, we can divide over here and get t equal to 8 seconds. Okay. So there we have our time now. Right, if this was constant velocity, Zara, which formula could I use to find the displacement? If it was constant velocity, if the speed didn't change.
It would just be changing displacement over time.
Yeah, we could just use that guy, right? But unfortunately, the velocity changed, all right? And so we can no longer use that, right? But we just learned a very nifty formula for when we have a change in velocity, right? Our displacement is equal to a half, right? So we're going to take the average velocity and we're going to multiply that by the time. Okay, remembering that this here is not speed, it's displacement, right? The easiest way to remind yourself when you see a formula, if it's displacement or speed, right? Speed is equal to distance over time, right? velocity is equal to displacement over time. So have a look at the variables that are together. If you see an S and a D together, it's speed and distance. If you see a V and an S together, it's velocity and displacement. So please try not to get mixed up between the two. Okay, just subbing in all the information that we know. Our final velocity was 9 meters per second. Our initial velocity was 5, and the time we calculated as 8. And so our net displacement was 56, right? This is displacement, right? It is just meters. Very, very difficult stuff, hey?
Incredibly
Yeah,
difficult.
like my brain is hurting right now.
I know. And when you do the homework today, your brain's going to hurt a lot. A lot.
Yeah, you know, we're gonna be stuck doing the homework for like an hour. Oh my word.
Yeah. So,
It's gonna be bad.
right. I know this is going to sound silly, but is there anything about acceleration that you are struggling to understand?
No.
No? Okay. So as I said, at the moment, we're only looking at constant acceleration, right? And that is why we're able to use all of these equations, right? If we did not have a constant acceleration, we would require a function, right? And that's, I think, outside the scope of this course, right? So there's your two formula for the day. Average velocity, right? It's just the initial velocity and the final velocity divided by 2. And if we want to work out net displacement works off the fact that we have average velocity. Average velocity comes from the fact that we have acceleration, right? If we did not have acceleration, we wouldn't have an average velocity. We would have a constant velocity, okay? And if we had a constant velocity, well, then we don't have to bother with all of that. We can just use our standard displacement equal to velocity time equation. Okay? So that wraps up today. There's your homework up at the top there.